Well, first of all, I want to thank the opportunity to share, to be in this wonderful workshop so far and share some of our work today. So I'm going to continue on what Melissa already started on understanding ice in star-forming region, and I want to focus on a little bit more evolved stage in the protocidative phase. So those are little kind of reddish, yellowish sources, very embedded. In star-forming region, have a lot of material, mostly gas and icy dust around it. And what we will try to figure out what are the composition of those matters going to be accreted on the protostar, and what are the connection to the eventual planetary systems. So Melissa already, all of our work I'm going to show in the rest of my talk coming from this free program. One of it is Karina, Webb, and myself. There's also Joyce Plus programs with combination of two GTOs, and there's also IPAs coming from a GEO program. So Melissa already gave a very nice introduction for ICE and how is it connected to our solar system and protostar. I'm going to skip this slide. Basically, this what we really try to understand about ICE composition is try to see what other connection there is between protostar stage to our solar system, and how come we have these ice composition protostar systems. So I want to focus on kind of particular strands of molecules that we see. These are what we call complex organic molecule. They're basically just a lot of atoms in the molecules and have carbons in there. And in the last decades or so, it's really advancement from ELMA. Like we see a very rich spectrums for kind of starting from several classes of very embedded protostars. So all of these lines we can kind of point out to the certain very complex molecules, so comps. And for very small number statistics, so comparing one protostar to one comet, we actually found that these type of molecules, their abundances is actually quite similar between protostar and comet. So that's another layer of kind of like encouragement saying that there could be some inheritance even for these very complex molecules. And this is also not just a few sources we have found these complex molecules in a few surveys that's been out. This is one of them that we did a few years ago. We do see these kind of complex molecules being quite prevalent in the population of protostars in Perseus in particular. We see about 60% of the sources have these complex molecules. But what really also very intriguing to us is that we have these 40% or so sources which don't have any emission for this complex molecule detected. So these are just saying we couldn't conclude that there's any existence of gas phase complex molecule here. And so then we start wondering like what's happening about these sources. Do they actually evolve differently, or there's some other processes that are preventing us to see them in the gas phase? So if I want to kind of like almost oversimplify these scenarios, I can kind of categorize these possible reasons for the lack of a gas phase comps in these two broad category. One of them is the chemistry actually evolved differently. So typically we think these complex molecules are forming on the ice. So this is my representation of icy grains. And at some point, this icy grain evolve and the comet will form on ice, and then it will keep falling down to the protostar, that's gravitational collapse. And the ice got desorbed into that gas phase, and therefore we can detect them. So a different chemical evolution, which just means that these icy dust just for some reason don't have these complex molecule form on the ice and get desorbed because there's no complex molecule in the ice, so we don't see them in the gas. So that's what I would call chemistry-driven scenarios. The other one is that there could be, for some reasons, we do have complex molecule form on ice, but for maybe the physics or the thermal structure of sources, they just don't get desorbed very easily, or they mostly remain on the ice for some reasons. And therefore, there are these complex molecule form, but then they kind of remain locked in the ice phase, so that we don't see them in the gas phase. And our argument with JWST, we finally have, we can kind of directly address these two kind of broad scenarios by directly observing the ice. So on the chemistry-driven scenarios, I think what we can do, as Melissa already showed some examples, is we can really figure out what are the composition of the ice in the protostatical envelope, and we can even connecting to that to the early cloud phase. So this is involving figuring out what is mixing with what, and kind of look into whether these composition of ice are actually favorable for the formation of complex molecules. And we can also look into ice processing in envelopes or heating events and to see how they change using the ice feature to see whether there's any processing in the past. I'm going to show a few examples in the end of this talk. In a distortion scenario, I think we can kind of do a very simple experiment that I would say it can only be achievable by JLFT. Is that, for example, we have two protostars here, and one of them, this is all characterized in the gas phase. One of them, we see gas phase emission lines, so we call it COM-rich. The other one we don't, so we call it COM-poor. But really what happened is that we really want to know whether these kind of diverse gas phase appearances actually coming directly from ice. Does the ice phase also have these kind of like differences that we infer from the gas phase? So those are, with JWST, I think we can directly tackle those question marks and kind of really figure out whether this inheritance is actually there or not. So the distortion scenario is sort of like the basis of how we put together this Carinos program. And so what we really try to do is we pick kind of 4 sources, kind of minimum sample to be able to serve like to sample 2 quadrants. So one is the COM-rich versus COM-poor. Those are determined by the gas phase. And the other axes are luminosities and basically as a proxy to ability for desorbing these icy molecules. So the image shown here is a Spitzer IRAC images, and with JWST we use mirror MRS mode. So we're looking at these small blue squares here and just show like kind of what kind of images that we actually have from MRS. These are the molecular hydrogen lines. So for the rest of the talk, I'm going to show a bunch of spectrum, and they're mostly coming from an extraction toward the protostars. But I want to take this opportunity to highlight that we do have spatial information already in our data, and there will really, I think there will be next steps in terms of game changer, like to take what we learn from a single spectrum and kind of see how we can push it in a spatial sense. So in the spirit of showing before and after JWST, this is what our 4 sources look like in Spitzer IRS, and this is what we have with JWST. And so this is basically getting a really high definition version of the spectroscopy that they only enable by JWST, and every feature's got really crisp. And we do see just all kinds of different ice features. Some of them are kind of quite well known, but with high sensitivity enabled by JWST, we can really dig into little minor features and kind of the bumps and wiggles in the ice absorption feature to further understanding the mixtures that are happening in individual sources. And so that's one thing that we try to do. This is work led by postdoc in Kasi, Jae-young Kim. Like he really tried to put together ice inventory in this RS-5398 source, which is the first source that we actually got our data on. And so you can see the red line here is our composite model. We kind of reproduce most of the absorption feature reasonably well. There's some underestimation around 6 microns or so, but I think this is sort of like one of our most complete censuses of ice inventory in at least one of the 4 protostars that we have. We also take a different approach, try to do a forward modeling. This is using this work led by Jenny Bergner, so she also do protostellar modeling. We can basically put together a semi-analytical model for protostellar envelope, and based on the temperature of those kind of cells, so we can assign different ice abundance or composition in there, and we can basically try to see how well we can reproduce our observed spectrums. And this is showing that we can also dig into the effect of the properties are showing here 3 different models are varying different maximum dust grain size. So we can see they actually have a pretty significant difference in this 15 micron CO2 ice. And so the exciting part that JWST really enables us to do is to dig into this, what typically an ice people will call the COM fingerprint region around 7 to 8 microns. And so basically a very complex or kind of often blended distortion patterns. And so we'll recently put out a paper that really nicely summarized these absorption features in 2 protostars, where they found that they can be reproduced by a combination of various different complex organic molecule ice. So this is really the first time we can kind of quantitatively measure what kind of ice is coming from a complex species and how much there are. And they also see that there's some parts of these absorption features really susceptible to the choice of baseline fitting. So there's a lot of systematics actually going here. And in their paper, they actually go in great length about discussing all the systematics and affecting the result. And since we have this kind of complex molecular abundance measures of the ice, we can directly compare to what's happening in the gas. And what they found is that I actually found very comparable abundances in both ice and gas phase. And so that will point, like, kind of further supporting some inheritance scenarios. And in our source in 15398, we also have this range of spectrum, and they all kind of show somewhat similar patterns. And we're able to kind of reproduce this absorption with also a combination of complex organics, and we're still working on trying to robustly verify it. And one thing we found is that this is what we call COM4 approach, meaning they have very little complex organic molecule emission, but we do see quite abundant complex molecule in ice. And actually, if we look at column density, it actually makes sense, and they're quite consistent, and which just means that the fact we have very little gas phase emission just means that they have very little emitting area, so they're just faint. And if we look at these part of the patterns in our samples, I want to draw the attention to these two protostars. So L43, which is in green, and 15398 in orange. They have basically the same spectrum here, which would suggest a very similar ice column density for this kind of combination of different complex organic molecules. And if we go back to this cartoon that I put out earlier, that so this is basically two sources, right? One of them is COM-rich. We know it's for L43. The other one is COM-4, 15398. And in ice phase, now we know that they actually have very similar ice abundances and ice column density. So that just means that the fact that one source becomes COM-rich just means that they have, I think it's very likely they just have very high luminosity, and therefore we can dissolve more molecules into a gas phase, then therefore we see that. And it's also search for a different flavor of complex organic molecule ice. So this is work by Nazari et al. They look into methyl cyanide ice, and it's very tricky business and a lot of blending, but they're able to put out 3 tentative detection of these nitrogen-bearing columns in ice. And we also can see thermal processing feature, particularly looking into pure CO2 in not just normal CO2, but in CO2 isotope log. This is 13 CO2. So and Nishanti Brooklyn then did analysis for 5 protostar in IPA programs, and it's kind of like consistent with the fact that the more pure CO2 we have, it actually correlated with luminosity. So this is a further supporting the pure CO2 as a trace of the thermal processing. And with JWC, we can really look into really faint features. So this is kind of like HDO is like one thing that a lot of ice people try to look into the moment they get their data on, and it's really difficult to see. But through a lot of checking and also rolling out possible intruder or contaminations, this is very recent. What I think going to be submitted today, that Katie actually be able to argue that these 2 sources and the 4.1 micron features, that's actually very likely due to HDO. Actually, there's a 2 component of HDO. There's amorphous and crystalline HDO here. So I just conclude here that we really are kind of on the first steps of learning ICES and kind of in a new era of ICES in protostars. And we can really go from one spectrum to a spectrum map, which I showed nothing of that, but I think all of the analysis I'm showed they can be really easily, or it can be in the future, in the near future, we can really do it in a spatial sense. And we can kind of move from detection of ice mixture to a distribution of ice mixture in a protostar. So I'll stop here and take questions. Thank you.